Good morning, lovely 12s. Right, buddies, today is our big day. We get to start a brand new unit today. And the new unit that we're starting today is mechanics. So not even a new unit, I should say a whole new module today that we're going to do mechanics. Now, I absolutely love mechanics. It's amazing. I feel really lucky I get to teach it because, believe it or not, mechanics doesn't actually belong to us as mathematicians. It's straight up physics, so I'm really lucky that I get to teach this. Like, oh, I've loved physics all the way along, all the way when I was young and everything as well, and I think that you guys will love it too. I hope. So, yeah, very cool. So our topic is, so the topic that we're going to do today is called kinematics. Now, unfortunately, this isn't actually mentioned ever in your textbook, and I mean it should be, because that's what it's called, but yeah, kinematics is your title. Now, what kinematics is, my buddies, is it's actually studying like how things are moving, okay? So accelerations, speeds, distances, all sorts of good stuff. If you can throw something in the air, you can model how it works or how it moves with kinematics, okay? So it's studying like how things are moving. So this motorbike guy is moving around and it's studying how he's moving. So kinematics, that's what we're going to start with. Just why I like mentioning kinematics and calling it kinematics, even though the textbook doesn't, is because kinematics is actually half of the great big topic of mechanics. There's another topic called dynamics, which we'll also do this year, which is like forces and why stuff moves. And kinematics plus dynamics equals mechanics. And that's how come it's called mechanics, because it's kinematics and dynamics together, and that's exactly what we're studying. So how exciting! Cool! Anyway, let's start looking. Okay, so here we go. To start with, I've got just this little picture of Bart Simpson running to school. Now, I just show this picture because I want to get some terminology out of the way. You don't have to be too worried about this in maths, but I know in physics they're always very worried about this, but I'm just going to make sure we get it right because they can throw some trick questions at you in maths as well. It's not just in physics. So here we go. I've got Bart Simpson running to school and he's taking this wonky, scribbly path that is 3 kilometers long. The school's only 1 kilometer away, so like he could, if he had gone in a straight line, or if he were to run through people's back gardens or whatever, he'd have been able to get there in 1 kilometer, and it takes him 30 minutes to get there, is what the question says. So really quick, my buddies, I just want to get some terminology out of the way. Distance, you all definitely know what this is. This is just how far you've gone. So how far you've gone, okay? Now, how far did Bart Simpson go when he was walking? Well, 3 kilometers is how far he went, buddies. So how far he's gone, it's just 3 kilometers distance. Doesn't take into account anything like direction or where you started or anything like that. It's just how far have you gone. If you were going from Ulster to Stratford, that's like 8 miles. So if you went to Ulster to Stratford, that'd be 8 miles. Then you came from Stratford back to Ulster, that'd be 8 more miles, and you'd have 16 miles in total, and that would be your distance. Now, displacement, on the other hand, is almost the same. So they're almost, people use them interchangeably when they're speaking about them, but actually they're not the same thing, and sometimes you can get caught out by it, but I fall prey to it as well. I call displacement distance all the time. It's difficult to not, but displacement is different. It's how far you've gone from where you've started. From where you've started. Okay, that's one way to think of it. So that's 1 kilometer, because while he did do it a roundabout way, he only is 1 kilometer away from where he started. So it's 1 kilometer. Done. Displacement. Another way you can think about this is it has direction. Okay? Has direction. Which means the displacement technically is 1 kilometer. I can't put an arrow to the right. I've actually given it a direction. 1 kilometer east is how you normally give it. Now, in physics, you'd have to give that, this unit thing all the time. It's quite important that you define your direction. Usually in maths, we'll say positive is right, and then if the answer comes out positive, it will imply that you are to the right. That's usually what we do. Cool. 2 more words really quick. These two are also kind of interchangeable, but not quite. People say speed, even though they probably shouldn't. Speed is just this. It's just how fast you're going. How fast you're going. Cool. It hasn't got a direction. If you're looking down at your speedometer or driving on the motorway, it might say 70 miles per hour. And if it says 70 miles per hour, that's nothing to do with directions or anything like that. It's nothing to do with displacement. It's just like, how quick am I going at this very second? 70 miles per hour. Boom. It's like straight up, normal one. Cool. Velocity, my buddies, it's how fast you're going in a direction. In a direction. So this would have to be a little bit different. You'd have to be like, okay, I'm going, say I was going from, let's say I was going from, oh, watch me get the direction wrong, well, this would be embarrassing. Okay, say I was going from Ulster to Stratford. I could say, going from Ulster to Stratford, that my velocity is 50 miles per hour east. My speed would just be 50 miles per hour. Cool? Velocity is what's called a vector quantity, and that means it has a direction. Okay, it means that it does matter where you start, it does have a direction, and velocity is linked to displacement. Now the scalar quantities, the other ones that don't have a direction, are speed and distance. Okay, the purple ones are linked and the yellow ones are linked, and that is pretty much that. I don't want to get bogged down in it though, even though I have just got bogged down in it, and let's just get a wriggle on past that. It's okay. They'll try to confuse you a couple times, but I think I found a question that will show you when it's a trick question. Cool. We have one formula, your very first formula. This is for constant velocity, okay? This is something moving at constant speed, at constant velocity, okay? Now, you know this equation, even though you don't know this equation probably in the format that it's written right now. And this is just speed equals distance over time, my buddies. I know that you might not be able to spot that straight away, but this is just speed equals distance over time, because actually u is the velocity, or the speed as you would call it usually if they were doing it last year. The velocity, my buddies, is u. Now they don't use v, even though that would make sense for velocity, but you'll see why really shortly, okay? So it does need to be u, it's important that it's u, okay? It's v we use for final velocity, actually, you'll see that shortly, and u they usually use for initial velocity. T is time, and s is your displacement, okay? Now I just call that SUT, because that's what it spells, and that'll help you remember it, because we'll do SUVAT later, and that will be another thing that you'll get to learn and use. So it's just SUT, my buddies. Happy days. S equals UT. Distance equals speed times time is what that is, essentially. If you were to use the non-posh vector ones, it would just be distance equals speed times time, which is true, or speed equals distance over time. Cool. So let's do it. A person drives southeast at a speed of 60 miles per hour. They drive for 50 miles. How long did the journey take? And then if they drove 8 hours, how far would they get? What's the velocity in kilometers per hour? What's it in meters per second? Okay, you guys ready? I think you probably don't need me, so I think you should pause and just try it. Go. Okay, and if you did want me, here we go. How long did the journey take? Well, here we go. You only know one equation at the moment, S equals UT. Cool. Now, what was the question? How long? So we're after time, and it says that they go for 50 miles. Now, miles and miles per hour match up, so I can use these units, and here we go. Well, the distance then, the displacement is 50, the speed that we're going is 60, and t is time, t. So it's just 50 over 60, 5/6. What does that equal? 50 divided by 60, because we don't want fractions because we're not mathematicians anymore, we're physicists now. So I've got 0.83 hours, because the unit's going to be hours, because everything was in miles and hours. Now, because that doesn't seem sensible to me to have 0.83, what I'm going to do is I'm going to times that answer by 60, and then that gives me 50 minutes. Which makes more sense, doesn't it? Cool! Happy days, eh buddies? So you can just times it by 50. Cool. B, if they drove for 8 hours, how far would they get? Well, SUT, S equals UT. Now, if they drove for 8 hours, how far would they get? We want S, U is 60, T is 8. So nice and easy, this one 6 times 8 is 48, add a 0, and what's the unit going to be? Well, miles. Happy days. C, the velocity in kilometers per hour. Well, if you're going to go in miles per hour to kilometers per hour, you need to just know how many miles are in a kilometer. Now, lots of people have like 5/8 or 8/5 memorized. I have memorized 1.6, which is the same, and essentially 1 kilometer is 1.6 miles. So if you're going 60 miles per hour, it's going to be more in kilometers per hour because if ever you've looked down at the speedometer of your car, you'll know that. It needs to be more, so it's times by 1.6. 60 times 1.6 equals 96. 96 kilometers per hour. Now, there used to be tons of questions about conversions, but there isn't as much now, so I might just kind of cut to the chase here. Here we go. If you want to get in meters per second, here's what you're going to do, buddies. You always start with your kilometers per hour one. I'm even going to write it. Okay, kilometers per hour to meters per second. It's got a conversion rate of 3.6. So if you want to go from kilometers per hour to meters per second, what you're going to do is you divide by 3.6. Now, I bet you'll be able to know why it's 3.6. Oops, 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 oops. Which means to go this way, it's times by 3.6. Cool beans? Now, 3.6, I bet you can tell why, because now that we're in metric units, how many kilometers or how many meters are in a kilometer? Well, 1,000. How many seconds are in an hour? Well, 60 minutes per hour and 60 seconds per minute. 60 times 60 is 3,600. So we have 3,600 divided by 1,000 to make 3.6. So that's where 3.6 comes from. So anyway, 96 divided by 3.6 equals 80 over 3, which is 26.7. 26.7 meters per second, okay? And that's it. There's not a great deal of conversion questions, but it is good to know those conversions. And yeah, happy days. Cool. Rocking swiftly onward. Let's get on to some of the meaty good parts of this. Next thing I want to get you to write is this. Displacement time graphs, buddies. Now, these displacement time graphs look like this, okay? So displacement time graph, so in other words, it's like a distance time graph. Now, I know that you've learned this lots at GCSE, but I don't want anybody to feel like they don't know what's going on, so I'm going to help you with it. So, sorry if it's too slow, my lovelies. Here we go. Displacement time graphs. Now, here you go. This here, on the y-axis, I have displacement. So displacement is how far away you are from where you started. So that makes sense that the thing is starting at 0, because it means you started at 0. And then we've got the time along these. So if you were to take the coordinates that I've given there, then this actually would be 30, because it's a y-coordinate. That'd be 10, that'd be 2, and that'd be 6. Cool? Now I think the first question is what do those mean, but let's just make sure it is. Yeah, okay, great. What do those points mean in real life? I'm not going to write it down because it's going to take me ages. So I'm just going to say, have a look at the 2 and the 10. Just pause for a sec and tell me, what do you think 2 and 10 mean in the context of this question? Okay, well here's what it means then. It means that at 2 seconds, you've gone 10 meters. It's just a matter of reading it from the graph and knowing what the units are. At 6 seconds, you'd gone 30 meters. Cool. What's the gradient of the line? And include units. So this is just to get out what this is actually doing. Get the gradient for me. Well, we've got these 2 points, and just like you would in year 9, just for now, because we are going to cut all this out later, just for now, let's just do it, okay? Gradient, okay? So it's y, you know how to do gradients. So it's y2 take y1 equals, or over x2 take x1. So here we go. 30 take away 10, so that's 20, right? And then this is going to be over 6 take away 2, so that's 4. So what were we measuring when we went height-wise? Well, we were measuring in meters, just to include the units, just this once. And then what were we measuring when we went across? Well, it was in seconds. So what we've got overall then, my buddies, is 30 take 10, which is 20, over 4. And then the unit is meters per second, meters over seconds, which means it's 5 meters per second. So guess what, buddies? What does the gradient, then, of a displacement time graph represent? If you were to do the gradient of this on a displacement time graph, what do you get? Velocity! Cool, can you see? Because the unit is meters per second. It's how fast you're going. It's how many meters are covered per second. So it's velocity. The gradient of a displacement time graph is velocity. Cool, that's what I was hoping that you'd see, because that's going to be critically important really soon. Now here you go. Write a sentence about a person's commute that could describe each graph below. I'm going to say it really quick after I reveal them all, but just to start with, here's how this could look. Started from home, Started driving away from home, stopped at the shop, waited a bit, then drove further away from home. Perfect. See what I mean? Just to make sure you get it. What would that be? Okay, how about this? Drove to school, did school, drove back home from school. Ended up where we started. See, on the y-axis, we both ended up where we started. So it means we came back to where we started. Cool, you guys think about those two. Cool, well, how about this one then? Started at school, not at home, because home can be 0. Started at school because you slept over at school or something? I have no idea. Okay, started at school for whatever reason, and then drove home. Done. Cool, waited a bit, drove home. How about this one? Started at school, waited a bit, started driving home, forgot something, started driving back to school but didn't quite get there, realized you actually had it all along, started driving home, got to where your house is, and then forgot and drove right past your house to somewhere else. So that's a really jaggy, weird journey, but that would be a sentence that describes it. So I hope you kind of understand what it's getting at. Cool. Right. One more. I feel like I'm doing lots today, but it's going to be good. Okay, next thing. Velocity time graphs, okay? Velocity time graph. Now, velocity time graphs are just the same as displacement time graphs, but the y-axis contains velocity rather than time, okay? So, yeah, time's the independent variable every time, so velocity is here. Now, if you look at this, what kind of velocity, what's happening to the velocity in this picture? What's happening to the velocity? Well, nothing. It's staying exactly the same as horizontal, right? This is actually a constant velocity graph. This is somebody who's already driving at motorway speed and they're not changing their speeds. They're not accelerating or anything. They're just chilling at that speed. And here's what I'm going to get you to do with it. What do the points mean in real life? Just like last time. What would the 220 mean? That's right. If you said at 2 seconds you're going 20 meters per second, that's brilliant. And at 6 seconds you're also still going 20 meters per second. That's brilliant. You just get it from reading from the axes. Now check this majestic thing out. Here's something that might surprise you. It says find the area under the graph between 2 and 6. Okay. So it wants us to figure out this area here, and this could surprise you. I'm not all the way sure if it will, but this might surprise you. I hope it surprises you. I'm not sure if it will, though. Let's check it out. Find the area under that graph. Well, how tall is it to begin with from the floor up to there? Well, 20, definitely, right? 20, and it did say include units, so 20 meters per second. Just I stole that unit from there, get me? That's the meters per second up and down, and so that's why that's there. Cool? Now, how far left to right, buddies? 2 to 6? Well, it's 4. What's the unit? Well, seconds. How come it's that? Because I've nicked this seconds from this seconds. Cool? So I've just copied the units. So if you're going to find the area underneath, here's what you're going to get. Area is going to be, and with the units, it's going to be 20 meters per second times 4 seconds. Cool? So the numbers are boring. Nothing exciting happens there. 20 times 4 is 80. That's not very exciting. But here's what is exciting. Look at the units. Meters per second times seconds. Well, cancel, cancel. You're left only just with meters. What does the area underneath the velocity time graph represent? It represents displacement, buddies. That's a mega result. So if you get a velocity time graph, the area under it represents displacement. Cool. So there's all the technical bits done. I hope it's not too bad. I don't think this first lesson will be too bad. And I just want to do 3 practice questions with you actually from your textbook to see if you guys can do it. So I do think you could probably do most of these without me. So do feel free right now, pause and try, but I am going to do it in a minute. So you ready? Pause. Okay, and if you're doing it with me, let's do it. The cyclist rides in a straight line for 20 minutes, so that's that part. Okay, so she's going away in 20 minutes. She then waits for half an hour, then returns in a straight line to her starting point in 15 minutes. This is a displacement time graph for her journey. Work out the average velocity for each stage of her journey. Okay, so for each stage of her journey. Well, let's do it. Let's do this stage first of all. Let's call this one stage 1. Okay, I'll call that little section there stage 1. So I'm even going to split it off like that. Okay, So for stage 1 then, buddies, well, what are we going to do? What's going to be the average velocity? Well, how do we get velocity, buddies? Based on a graph. Well, if you said it's a displacement time graph, it's the steepness, it's the gradient. You're dead right. So are you ready? Her average velocity is just going to be this. It's going to be the gradient. So are you ready? Let's do it. Oh, I'm trying to think if I want to use m for gradient or if I want to use u for velocity. I'm going to use m because it's a question about... I'm going to use u for velocity to teach you how to use velocity as that variable. The velocity is going to equal this. It's going to be the total displacement, which is 5, over the total time. It's the gradient, so it's 5 over 20, which is going to be a quarter, 0.25. Now what's the unit on it? Well, it's going to be kilometers per minute. Cool. Oh, and it wants it in per hour, actually. So, kilometers per minute. What we can do then is we can just times this answer by 60 because it's 60 minutes per hour, and that would cancel the minutes. So I'm going to go times 60 minutes per hour, and then you can, I'm only doing this, you can skip that step, but I'm just doing it so you can see why it'd be kilometers per hour. So 0.25 times 60, 15, yeah, it is 15, 15 kilometers per hour. Cool. B is a good question. Write down the average velocity. Oh, for each section it said. Okay, so for section 2, I haven't finished A yet. For section 2, what's her velocity? Well, 0. 0 kilometers per hour because she's stationary in that one. And then for C, for part 3, what are we going to get there? Well, it's going to be, I'm going to use a negative. I'm actually going to let it be negative, so her distance back is going to be negative. Here we go. Well, we're going to have on this one, she's going 5. I don't want to do it this way. That's okay. I'm going to do it this way anyway. I'm going to be consistent. I don't like this introduction chapter. I'm not going to lie, but I'm going to be consistent for you, my lovelies. So help me, even though I don't like it. Here we go. The displacement that she goes is, I'm going to call it -5, okay, because she's going 5 backwards, yeah? So she's going down by 5 to represent the negative gradient. -5, and how long does she do it for? Well, 50 to 65, so it's 15 minutes, okay? 15 minutes is what she's got. So that's it. So what we're going to get there is, that is right? 6:15. Yeah, that's right. So then we're going to get there. Let's do it with a decimal point because we are a physicist now. So it's a third, so it's going to be 0.33 by -5 divided by 15, 0.33. Of course it is. So -0.333. Now what we got there, though, again, is kilometers per minute, but we wanted it in kilometers per hour, don't we? We need it in kilometers per hour. So what do we times by? Well, we're going to times by 60 because there's 60 minutes per hour, and that cancels out the minutes. And so that means you just times it by 60 and you're going to get 20. So -20, and the units now are kilometers per hour. So +20 was her distance away, and -20 would, this, here we go. This +15 is positive as she's leaving her house. This -20 is negative because she's returning home. There's the direction convention happening, buddies. Cool. Work out the average speed for the whole journey. Well, buddies, this is just trying to get at the other thing, average speed. What you're going to get with average speed is just going to be this. It's the total distance over the total time, because we don't want to care about directions then, okay? So average speed, it's just the total distance. So it's how far you've gone over total time, okay? So direction doesn't matter anymore. So if we want to get her speed, how far has she gone? Well, she went 5 in this first section, so she went 5 kilometers away. She didn't go anywhere in the second section, and then she came 5 kilometers back. So altogether, she's gone 10 kilometers. How long did it take for her to do it? Well, 65 minutes. See what I mean? From the bottom, that's literally it. 10 divided by 65 is going to be 2/13, which is 0.154. 154 kilometers per minute, but it probably wants it in kilometers per hour because that's a weird unit, times 60, because that would be minutes per hour, and that cancels the minutes. So times that by 60, and you get 9.23. 9.23 kilometers per hour. Boss. Cool beans, buddies? Sick. Swiftly on, my buddies. Swiftly on. Next thing. This figure shows a velocity time graph illustrating the motion of a cyclist moving in a straight period for 12 seconds. For the first 8 seconds, she moves at constant speed of 8 meters per second, or 6 meters per second. So she's going at constant speed, so she is moving for the first 8 seconds. And then she decelerates at a constant rate, stopping after a further 4 seconds. So we can tell there's 2 phases in it. There's this, where she's at constant speed, and there's this, where she's decelerating. Now, find the displacement from the starting point of the cyclist. Okay, good. Here we go. Displacement, buddies. How do you find displacement from a graph? From a velocity time graph. How do you find displacement from a velocity graph? Giving you a hint. Because meters per second is here, and seconds is there, and if you were to times them, they become meters. How do you do it? That's it, it's the area under the graph, my buddy. It's so cool beans. You got 2 options. If you just find the area under this graph, that is the displacement. So you got 2 ways. You can either treat it like one big trapezium, which is probably what I'm going to do, or you can instead do the triangle and the rectangle. I feel like a trapezium today, so I'm going to do a trapezium. So let's do it. Okay, displacement is variable s. Okay, in sut, in s equals ut. Displacement is the s, so that's what I'm going to use s for. And let's do it. It's a trapezium. A trapezium, in case you don't remember, is half the sum of the parallel sides times the distance between them. That is how you find the area of a trapezium. That's it. That's your formula. So let's do it. S equals half the parallel sides of the top and the bottom. So the top, how long is this part here? Well, that's 8 long. Cool, so it's 8 plus, and how long is this? Well, that's 12. So it's 8 plus 12. And what's the distance between them? 6. 6. So here we go. S equals 8 plus 12 is 20, halved is 10, times 6 is 60. 60 meters. Bang. Cool. Work out the rate at which the cyclist decelerates. Now, we've not even introduced this variable yet, but you know for sure that if you want to find acceleration, it's going to be, how are you going to find acceleration? It wants to know about this part. Well, how do you reckon? Meters per second and seconds. That's it, it's meters per second. So what you're going to do is just this. You're going to find the gradient again, okay? It's another one of those gradient questions. Now, if you want to do the gradient, here we go. The gradient, which is actually going to be acceleration, which I'm going to call A, it's going to be this. Well, it's going to be negative. So first things first is how far down does it go? Well, -6. And how long does it take to do it? 4. So we've got -6/4, which means, just the calculator, divide by 4, oils, -1.5, like a boss. 1.5. And what's the unit? Well, it's meters per second, but there's an easier way to write that. It's this, -1.5 meters per second squared, which is my preferred way of writing that. But then the book also does this. It goes -1.5 ms to the -2. But that's a bit, you can use that if you like, but that was pretty much before they had online, that's better for typing, to write it like that, meters per second. That's better for typing because it only takes 1 line. But if you're writing it by hand, this makes more sense. Cool. Ready for your final question, your hard question, then I can leave you to practice a whole bunch of not too bad questions. Here we go. I think you should pause and try this one. Go. Okay, and if you don't want to, let's do it, my buddies. Here's what it says. It says a particle moves along a straight line. The particle accelerates uniformly from rest, so uniformly means at a constant rate, from rest to a velocity of 8 meters per second in t seconds. The particle then travels at constant velocity of 8 for 5t seconds, and then it decelerates. This is a terrible color, let's go green. And then decelerates uniformly to rest in a further 40 seconds, and we're asked to sketch a velocity time graph. Okay, let's do it, buddies. We can do it. You ready? Velocity time graph. Just looks like this. Okay, time along the bottom, velocity up this way. Cool. Now it says it starts off from rest, so it starts off at the floor. So from rest at the floor, and it accelerates to 8 meters per second after t seconds. So it goes like this in the first section, and that means that it's now at 8 meters per second after t seconds, which means down here, we don't know how long it's been, but we know for sure it's been t seconds. Cool? That's the first yellow part. It then travels at constant velocity, which means that our line is going to be flat, horizontal, you're right, for a little while longer, so it stays at 8, and then for 5 t seconds. So it takes it, so this is like t seconds, okay? And it brings us to t, and then it says it takes a further 5 t seconds. So where would that bring us to on the floor? That's it, 60. Cool. It then decelerates uniformly to rest in a further 40 seconds, which means down back here to rest, and that takes 40 seconds. Okay, sweet. I think that's perfect for our velocity time graph. Now, given that the total, here we go, this is where it gets good. This is a hard question now. So, happy with the graph though, okay, buddies? Are you happy with it? The labeling on the bottom is not terribly important, the t and the 6t, but the labeling each section is very, very important, so I hope you got your head around that. Okay, now it says the total displacement of the particle is 600, so where on earth do we put that in? 600 meters. That's the total displacement. So where does it go? That's it, buddies! It's a velocity time graph, so the area underneath is equal to 600. Cool? The whole area is equal to 600. Well, buddies, guess what? I could do a trapezium, but I think that's going to be too complicated, so I'm just going to do the areas of each of the sections. 1, 2, 3, because my trapezium is going to be harder algebra than just doing it. Now, we know that that's t, width. We know this is 8 tall. We know that this is 8 tall. And you're ready to crush it now. So you ready? Get all the areas and add them together. So, yeah, pretty much area 1 plus area 2 plus area 3 is going to have to equal 600. Well, let's do it. Area 1's a triangle. Half base is t. Height is 8. Half base times height. There we go. The rectangle in the middle is just going to be length times width. 5t times 8. And the third one at the end is a triangle as well. Half base times height. Base is 40, because it's actually given in this one. And height is 8. Cool? So there you go. There's all of them together. That is to equal 600. So let's bish bash bosh it through, my buddies. So 4t plus 40t, 20 times 8 is 160, plus 160 is equal to 600. Cool. So 40 equals 600, take 160, take 160 is 440. 440, which means that t is divided by 44, 10? 10! 10 seconds for this whole palaver, my lovelies. How exciting. That'd be an example of a hard one, folks. So if you get your head around that, no problem for today especially. You ready? I'm not going to give you too much to practice. It's these guys here. 135 first, because they're the velocity time graphs. Do a mix, but if you want to, like, do a mix of only the hard ones if you have your head around this. Like, just jump in at question 5, 6, 7, 8. 132, question 1 to 4 are displacement time graphs. I'm not too fussed if you don't try very many of them at all. Do like one of those, or 2 of them at most, because velocity time graph is way more important. You'll see soon. Cool beans, buddies? So, I hope that you liked your first lesson of mechanics, getting the kind of boring or rubbishy or little bits out of the way first of all, but it is cool, it is building to something, and mechanics is amazing, so I hope that you'll think that it's phenomenal by the time we've finished everything. I hope that you will. So, that's it from me, buddies. See you next time. Bye, buddies!